Hello and welcome to Big Ideas Only. Today, once again, we are talking about 3D printing. And in the last episode, we were focusing in on the practical applications of 3D printing and why it's not just a wish.com machine that you have on your, well, I was just about to say kitchen desk, but in your, I don't know where you would have it, in like your backyard or somewhere in that hobby room that you have somewhere. But it's also something that can really revolutionize industries and enable new components to be built that were just not possible to build before. Today, we are focusing a little bit more on the theoretical side. What is 3D printing actually? What makes it hard? What are the advancements? This is some of the stuff that we're looking into today, and this I'm really excited about. And once again, we have Kristoffer Ryelund Nielsen in the studio with us, and you're the head of engineering. And we also have Karl Frederik Fischer, and you are a PhD in material science. And also, I need to find the words, additive manufacturing specialist, and you both from the Danish Technological Institute. And we're here at your premises, so we've actually already had a little walk through the factory. That was without the camera, so I'm sorry you guys out there. But I think let's try and dive into the theory behind this. Maybe start with the top layer. What is 3D printing? How is it actually done?
Nice segue. First layer. Building layers.
Oh, yeah. Thank you. I'll take it.
Yeah. Nice done. Yeah, so basically, we often call it 3D printing. We print stuff in 3D, but it's also called additive manufacturing, which means we add stuff on top of each other. We build layers from the bottom up, instead of subtractive manufacturing, where you have a block and start removing material. So that's actually just what it means. It maybe sounds a little fancy, but we just put layers on top of each other. It's really hard to do with some materials, but you can do it with a glue gun at home. That's also 3D printing. Or you have maybe back in school made it with clay, these putting
clay sausages
on top of each other. Yeah. It's also additive manufacturing. Now we just have a computer layer putting the layers out.
And how? What layers are we talking now? Because we have some titanium parts, we have some copper parts. What's this?
Titanium as well.
There's titanium as well, just gold.
Yeah, it's coated with a certain coating at one of our sister centers here at the DTI.
But how does this work? Because none of this looks like my clay creation.
So you have many different technologies, and all of what we have here is what's called made with a technology called powder bed fusion. So you have a very fine powder in a flat bed, and then it's fused together. And in our case, we use lasers to do that work. And then we are putting out like 60, 90 micrometer layers at a time. So it would take somewhere between 10 and 20 layers to just make a millimeter of height. So that's why you don't really see any of the layer features here, because it's too fine to sort of see with the naked eye. Like if you really look close and such, you can see it, and with some practice it gets easier. But that's why this is one of the technologies that is often used in industry, is that you have such a fine feature when it comes out of the printer that it's often usable as printed. But there's many other technologies for 3D printing, and as Kristoffer said, it's all just a question of adding material on top of what's already there, and that's what makes it additive manufacturing. And then
just to say, we use powder. It's a very small part of what you can do. You could also just have a big robot welding on top of each other. You can make much bigger parts than we can do. You can also have resin that is cured with UV light that can make small and very detailed, even more detailed than this parts, that is transparent, and it depends on what your needs are. And also, do you need one or do you need 1,000? Stuff like that.
Yeah. And what if we're talking about what you're building with here? sorts of materials are we talking?
So here we are talking, in front of us, that's a selection of our metal parts. We also have some polymer printers to print in various plastics. But it's all sort of conventionally known materials to industry, because that's what they are used to and expect. So that's what's sort of easiest to sell them. So on our polymer printers, it's a nylon, a PA12, very commonly used in industry. Some of these parts are a stainless steel called 316L, and a very common titanium alloy. It's all commonly known materials, because that's what people expect and know. So that sort of makes it easier to adopt a new technology when at least something is familiar to them.
And you can say it is a little complicated process to make this powder, this very fine powder that needs to be totally spherical. Each individual grain should be spherical. So you don't see a cheap material for a metal printer. You don't see carbon steel, something. Then you have 316L that is stainless, so it can be used more broadly. You can use it for the same applications, but you don't make 3D printed metal yet with less good material. So it's really high quality out of the machine, so very strong, maybe often actually more strong than if you mold a part or something like that. So that's also a common misconception. People think that, it's fragile and it's probably porosities and stuff like that. Not anymore. It's very strong and durable.
But what's happened on that part?
Optimization of the system. So the first machines that were built like 20 years ago, people were still sort of, how do we build or pick the right laser for it? How do we control it? And also computer technology wasn't as advanced back then. So it was a lot harder to have a computer that was quick enough at all of the calculations needed to have the level of control that was needed. And sort of laser welding to that extent wasn't as developed. But over the last couple of decades, a lot of development has been made in both the quality of the lasers, the quality of the mirror stages to control where the laser spot is. And of course, now I'm only talking about the technology we have here. You have the same development in other technologies that also has gotten a lot better. But it's sort of just a continual development of what do we need the technology to do to be able to produce the quality that we need, and how do we set the right parameters on the machine? What should the laser power output be? How big should the laser spot be? And how should it move? And then also as we found out what do we need, then we've started and more people has adopted it. Then you also have gotten a bit more scale of economy in making all of these mirrors to control where the laser spot is and such. So there's been more interested in pushing that, because while a lot of physicists has been making really complicated laser setups in various basements at physics institutes and such, it's a difference between having it in a research environment and getting it to a production environment, and getting that at a price that's not at a level of a research lab. Like it's sort of, there's a lot of development that's happened there.
Yeah, exactly. And a cool thing about that you mentioned, the price is coming down. So we see this trend that about 2009 or something like that, something happened. Something happened in this industry where suddenly the total world revenue of 3D printing just started to exponentially increase.
Why is that?
Because there were some patents that ran out. So we started printing in 89. Patents, they run out about 19, 20 years later. And then something just happened. All these cheap machines, the whole rip-wrap movement where we print a printer, and the FDM printer was now available for everyone. This is also happening with some of the patents on metal 3D printing now. So we see machines, the most expensive one we have out here, it cost 9 million crowns or something like 1.12 million euros, something like that. But now we see there are machines that cost 100,000 euros that can metal print. Not as big, not as fast, but something is happening here because industry wants to make money. But when the patents are done, we can see it becomes much more available, and the price are coming down, and competition and all that. So it's very interesting.
I'm guessing that's a very common thing to see when patents run out. And it is also, note, that is also the point of a patent, is to give the patent holder a chance to prosper from...
recoup their investment.
Exactly. Yeah, so a FDM printer in the 90s cost maybe 300,000 Danish crowns. Now you can get it on online Bamboo Lab for 2,000, 5,000 crowns or something like that. And they can do the same thing almost. So it's very interesting.
I'm wondering, to go back a little bit, I'm wondering, as a material scientist, what are you looking at out in the field of 3D printing? Maybe not only at the Technical Institute here, or the Technological Institute, but also what is happening of cool stuff right now in terms of materials used for 3D printing?
So some of the interesting things that's going on right now, to me at least, is one that more people are exploring multi-materials so that you can switch between the materials as you're printing.
Within the same string of...
it wouldn't be the same sort of string of material, but just that you have a system that can sort of deposit some of one material and then take from another part of the system and put another material, because that gives you another dimension to your design freedom, that suddenly you can start mixing materials. And of course, not all materials are compatible, but in a injection mold that needs to be of some kind of steel, so it has the corrosion resistance and such to the abrasive environment that casting is, you can start adding some copper segments within to increase cooling in key areas, lowering the cycle time and increasing output rates and increasing the value. Or you could, in other situations, you could have a core of steel and then with a surface of a expensive nickel alloy known as Inconel. And then you can get a much cheaper part by only using the expensive material where it's absolutely needed. And to me, that's like interesting, both as a technology and a potential, enabling that extra dimension of design freedom, but also...
So it's just to understand, it's like the 3D version of putting gold leaves over your whatever.
Yeah, exactly.
Metal structure.
But now you don't have to put it only on the surface of stuff. You can put it inside stuff. You can make it twist and turn just the way you want. And that is very cool. Imagine like an electric motor. There's a lot of copper windings in there, and there's some magnets, and there's some metal and stuff. Why don't print that maybe in one part where you just put the copper where it's needed and make it even more compact or something like that? Imagine instead of having 10, 20, 30 processes to make a motor, you can just print 2-3 different parts, put them together, and we're not there yet. There's a lot of stuff needs to happen before, but this is what's enabling that.
And you talk about, or we also mentioned in the last episode, we talk about temperature, weight, and you said flow improvement as well. Can you elaborate that a little bit? What is 3D printing pushing here in terms of optimizing for temperature and weight and all this?
Yeah, that's a good question. So why 3D printing is a good solution for that? On the weight side, there are actually two main reasons. Because you can make very strong parts that are lightweight if you use something called topology optimization. So you can use the software, as Karl talked about, that the software has gotten better, so you can make more intricate designs, and that is it looks kind of like bone structure actually. And it just happens to be that that 3D printing is often the only way to manufacture it. And the other side of it will be that when you 3D print, you only pay for the material you use. You don't start with the big block, as we talked about earlier, and start removing that. And every time you remove something, it costs something. Here you only pay for the material you use. So it allows for these intricate structures, and the more material you can remove, making it lighter, the less cost it will. It will be cheaper.
And can you explain the calculations that go into that, and maybe not into like how do you actually set up the calculation, but what is the aim of the calculations, the design?
So what you essentially do in the computer is say like I have this specific use case where I have some mounting points. Like an example we have in our exhibition, but somebody took it elsewhere, so I can't show it to you on video. But it's a wheel mount where you're saying, okay, I have this car. I need to mount this wheel, and here are my mounting points. And then I put in that, well, I know that there will be these loads and twists and forces affecting this in these mounting points. And then I have a big block in the software and some mounting points, and then I ask the software to find which part of this block that I originally defined is not needed to be able to withstand this load case that I then fit the software. Then it tries to iteratively remove a part, then resimulate, is this fine? Yes, okay, and then remove another part, and then it goes around and tries to remove material and shifts it around and does a lot of like optimization, moving where is the material within all of the bounding parameters that I put it with.
Is this something that is something that's simulated? It's not something that you can calculate like geometric.
No, not at all. It is an iterative numerical calculation where it simulates based on material properties whether it can withstand the load case now that part of the material has been removed.
Yeah.
Okay.
So that is if. So that is if you want to optimize for only the strength of it or reducing the weight. You can also tell it needs to be as stiff as possible. So optimize. You just tell it the computer what you want to optimize for, and it will give you the best answer possible. Of course, you always need to be aware of what you're doing, because it can also it will come up with something. If you put shit in, you get shit out, right? Yeah. So you need to know what you're doing. It's still not just plug and play, but it's definitely something. The new engineers, they will get this in this, learn this in the school.
Before this interview, we talked just a little bit about the different materials that's available. And then you mentioned what do you call it? Moon dust? No.
Yeah, I couldn't find a source for it. I thought it was called moonium, but it's like the technical name is lunar regolith simulant. So artificial moon dust.
Moonium is so much cooler.
Yeah, let's call it moonium. That's right.
Yeah,
absolutely.
I'm pretty sure I've seen somebody call it moonium, the synthetic moon dust.
And why is this a material that's interesting? Can you elaborate that?
So, as we also touched upon earlier, the space industry and opportunities in space, there's a lot of interesting options there and potential. And it's long been a dream for a lot of people to start getting a permanent human presence somewhere beyond Earth. And being able to print...
Yeah, we've kind of heard that story before from several billionaires.
Yeah, exactly. and part of that would require being able to build something on not Earth. And then if you can do that in the materials that are there, that would be significantly easier. So that's why a lot of people are looking at synthetic moon dust and synthetic Mars dust and trying to actually produce parts in those materials, trying to figure out, well, can we bring some additives, make a cement, or how can we melt it in various ways, make it stick to itself, and really looking into what 3D printing technologies and which manipulation methods do we have given the materials that are present in the locations where we actually want to build up a presence. And that's where
actually, now thinking about it, you don't even have to go beyond Earth for that to be a good thing to be able to do.
No, not at all. It's
like
just
you could just go somewhere that's
just
like go to the Arctics, somewhere where it's really a pain to get stuff.
Yeah, so this is just a logistical problem. If you had an injection molding machine or a brick layer on the moon, use that, but you don't. You don't have that in Antarctica as well. So this is a logistic problem. So anywhere that is very hard to go or very expensive to go there, and it's more expensive to bring stuff with you, why don't just print it where you need it, when you need it? You're also more practical example talking about why, but maybe we could put printers out on all the big freighter ships so they can print their spare parts and keep the boat running. So they don't have to go into port and stuff like that. This is just to the extreme, printing on Mars. But it also works on planet Earth, yes.
Yeah.
But I feel like printing on Mars, it will still be, well, you only have like Mars sand.
Yeah.
And the same goes for moon dust. You only have moon dust. There are no trees. Well, you can probably extrapolate some materials from that dust, or how would you actually do it? Or is it only like feasible to think, oh, we can make some sort of cement?
It's not only feasible to think we'll make some kind of cement, and it will also depend on where on the moon or Mars that you land, because as we know from Earth and all of the sort of probes that we've sent to the planets, it's not just one material all on the surface all throughout. Like there's material variations depending on where you are on the planet or on the moon. So there would be a question of, well, where will we land? What materials will we have available? And then will we use what is right on the surface, or will we dig down and take something that's like a meter or 10 down underneath the surface and use that? And then you have a lot of material processing that could be possible. And of course, the more steps you add to your process, the more complicated it is, and the more vulnerable you are to issues in your deployment. So that's why a lot of focus is on these cement solutions, because that's the simplest solution to sort of make. It's very easy to move a paste around and extrude that in a controlled manner and make something out of it. But in principle, there's also a lot of melting technologies being explored, and there's people talking about, okay, if we really want to make something that can perform in various ways, maybe we need to do some refinement, and what would that then look like? And some of the refinement things that are being considered looks at what materials do we have available and what chemistry do we know that will allow us to take, well, this material is highly oxidative and we need to oxidize this, or the other way around, reducing and reduce it. And look at what sort of materials that we can find here can we use to produce the feedstock that we want to print with. But
yeah, there's maybe also a step even before that, because as you mentioned, it could be you need a whole mining operation going on Mars before we get there. But another thing is just you can also.
It's not something that happens tomorrow. In other words,
not really. But something that is actually happening tomorrow or today is if we bring our own filament or raw material up there and print with that. And why would you do that? That could be if you don't know what you're gonna need. So you can bring a hammer up there if you know you're going to need a hammer. Yeah. But what if you need a screwdriver? Damn it. Then you have to send another one. But if you just have this raw material, then you can print the screwdriver instead of the hammer. So we're actually doing this already. We have been doing it on the International Space Station since 2010 or something like that in plastics. And just I think it's a couple of months ago, we printed the first metal part on the International Space Station. So Andreas Mogensen was the one. Yeah.
Pause.
Yes.
How? I've seen your machines out here.
Yes.
They don't fit.
Nope.
At ISS.
Nope.
They're like probably. I would estimate they're probably like 4 to 5, maybe 6 times the size of what will be able to fit in the space station.
Yep. It's a question of technology a bit as well. Like you can get machines that use powders like ours that are significantly smaller. But one thing is that space and very fine powders are not a good mixture. Gotcha. At least like when you have low gravity environments like the space station, maybe on the moon and Mars, like that's another conversation. But in the space station, having a very fine powder, that's
floating free in the air.
Floating free in the air.
Not good.
Not good. Very complicated very quickly. So that's all of the printing technologies that I'm aware of that we've had success with on the space station are all wire-based in various ways, whether it's a plastic wire in a filament printer like that we all know from sort of home hobbyists to these welding robots where you take a metal wire that you would normally use for welding and then just give a computer control over where does it actually weld. And the metal printing we've done on the ISS has been a wire-based welding robot.
Yeah, so it's the same size as a small fridge, something like that, installed up there. Of course, custom made to fit. And right now, we have brought the specimens back to Earth to test what does the microstructure look like when it's printed in space. We have no idea. To see, is it stronger? Does it bind better in almost zero gravity, or is it just...
Or are they more free floating?
Yeah.
Could be also.
Maybe.
Yeah.
It is tested at the moment. So that's very interesting. And another material that they are looking at printing on the International Space Station is actually something where it could be manufactured in space because you need zero gravity to make it work. That is something like organs or human tissue, where if you print it on Earth, it will tend to flatten out. It will be... It can keep itself up, so you can't really print it. But up there...
Yeah, you have to print it in zero gravity.
Yes, so it will just stay there and you can print it floating. And then when it's done, it can hold itself and you can bring it down to Earth and hopefully someday implant the new lung into a person. So that is...
but it's still pretty far out that you would have mass production of human lungs in space.
Yeah,
just transporting them back and forth through the atmosphere. It seems like
it will definitely make a market for space travel. Have to send stuff up there. But yeah, they are actively looking into it, and they have a prototype thing on ISS right now where they try to see what can we do with the tissue up there. Very interesting stuff.
That is really interesting. What are you looking most forward to, say, looking 5 years ahead? So short future.
Yeah, so we of course look a lot of industry applications. So what we see is it will just become more and more available. So the prices are going down and the machines are getting bigger and faster. So yeah, incremental small steps towards being more adopted. So I think someone said that we have today 0.01% of everything is 3D printed, everything produced. And someone estimates that it will get to somewhat around 5% of everything. So there's a lot of room to expansion here, but not everything should be printed in the future.
And I saw when I posed that question, your eyes went into like a researcher mode. A little bit dreamy, a little bit. This is.
Yeah. What do I look forward to? Because like I'm clearly in the research and development section of this enterprise here. So I'm a lot more with a sort of.
You're the dreams.
The dreams, the big ideas, that kind of thing. And I'm really looking forward to all of those things where we're really gonna push the boundaries of things, and we've seen a bit of it already in terms of material development, where we've touched upon it a bit briefly, where the materials that we mainly see right now are materials that people really know and have experience with, because it's a new technology, and then using something that we are familiar with is easier for adoption. But now that people have kind of gotten comfortable with the idea of additive manufacturing as a production technology, people are starting to ask the question, well, now that we have a unique production method, what materials can we use that cannot be used in any other ways? And one of the early examples of that was NASA working on copper alloys for the rocket engines. Now there's some companies that are looking at various aluminium alloys that I'm aware of, where you can't produce a part in that material in any other way. It is.
Why is that? But try and just explain briefly.
So it becomes in simple terms, it's a question of the material that you use is actually metastable. So it's not really stable, but because this production method, when you melt the powder with the laser, it's only molten for like a millisecond or less. So you don't really get it going to the sort of thermodynamically stable situation. It keeps being locked in this shape that it has. But if you were trying to make it in another way with like casting or something like that, the cooling rate would just be far too slow, and you would have a separation of phases that would then mean that you would not get the properties that you actually want.
Maybe it would crack or something like that, right?
And not these materials. They would just sort of separate, and you wouldn't get the benefit of having the particles that are kind of trapped inside the other material. So it's sort of on a microscopic scale. What happens is that you get a metal matrix of some kind, like just sort of you have a pure metal, but then in it you have some nanoparticles of the other materials that were then dissolved in the metal that precipitated out as small nanoparticles, giving you completely different properties. But if you tried to make that by casting all of these nanoparticles, it wouldn't cool fast enough to form nanoparticles.
They wouldn't get trapped.
They wouldn't get trapped. They would just end up finding each other and become big agglomerates. And then you would kind of just have something that isn't really that useful, because you don't get the effect that you want with these nanoparticles being trapped inside.
Yeah, so basically now, in the near future, we'll be able to produce alloys that have specific properties that you cannot replicate in a traditional manufacturing way.
Yeah, potentially. Like there's some alloys that.
Where do you think? Who would benefit from that? So, is that like everyone? Is it in computer industry, or who?
So it depends on what we are able to create these special alloys for, with which properties we can make them. And the alloys that I've seen so far that people have come up with, there's the one that NASA came up with for additive manufacturing, the copper alloy. That would be any like complex thermal management system where you need internal flow channels to do some efficient cooling, like a rocket engine. That could be the use case of that kind of alloy. The other alloy that I've sort of looked at, that creates an aluminium alloy with a very high strength and corrosion resistance. So a lot of places where we currently use high performance aluminium alloys, maybe now we have a better option for some of those cases. But it's a very complex question, because it's not going to be outperforming what we already have in all parameters. We're not going to get like a super alloy that will outcompete all other alloys. That's not going to happen. We are just, again, going to get another toolbox that gives us a better option for some specific use cases. So it's in addition to, now we get a new possibility that allows us to do some things just a little bit better, a little bit more specialized and higher performance that allows us to push some of the boundaries.
I mean, like polymer composites didn't replace metal. And the same here. These new alloys not going to replace old alloys. They're just going to allow new use cases and new things.
Yeah, and actually, we always ask people to say, what is the problem that you want to solve? Instead of saying, what materials can you print in? Yeah, but what do you need? Maybe we can tailor a material. Maybe we can find a solution that is perfect for that application. So you get a lot more freedom in, I need it to be very strong and light and conduct heat very good. Okay, let's try to say if we can make some aluminium alloy that can do all of that. So yeah, come with all the questions, and Karl will see what he got.
and then we'll put Karl on the job. I think let those be the last words for today. Thank you so much for joining us, Kristoffer Ryelund Nielsen and Karl Frederik Fischer. Thank you so much for joining in on this very interesting conversation. I think personally that when we see this shift, we talked about the patents kind of wearing out soon. When we see that shift, that's always something that will boost not just how many items are sold, but also what is sold and what kinds of. It always boosts stuff, which is really interesting.
Exactly.
And to you guys out there listening, thank you so much for being with us. And I hope you enjoyed this episode on 3D printing. And if you haven't heard it yet, go back and listen to the former episode as well, because that's on the more practical side, that's on the application side. What can industries and businesses actually do with this 3D printing technology and the cool 3D metal printing and all this? I think that's a very interesting one as well. And of course, if you liked it, share it with someone you think would also like it, and help us kind of spread the word, but also inform others about these kind of big ideas. That would be really great. Also, do leave us a review and hit that subscribe button. Got to remember to say that. Hit that subscribe button, hit the like button, all those. That really helps us spread Big Ideas Only across the globe. So that would be much appreciated. If you have any suggestions to what we should cover, or if you have any feedback, please do reach out to us on podcast@bigideasonly.com. That was podcast@bigideasonly.com. That email will land straight in my own personal inbox. So I will answer you personally. So do reach out on that email if you have anything that you find interesting. And I think with that, I just want to say thank you so much for being here.
Yeah.
And thank you so much for listening.